pointing down.
So, but that doesn't affect anything in how we set it up by describing.
This?
Yeah, that was just kind of like
yes. No, actually, this absolutely does affect. And you'll see, I'll show you when we go to parameterize this.
Okay.
We need to make sure that we get a normal that's pointing downward. If we parameterize this in the usual way, it'll point up.
Okay.
Yeah, so so this would be a more concrete example of what I was talking about at the beginning, about reversing the orientation of a surface.
Right.
Yeah. So because we can parameterize this base many different ways.
So the choice now was based on what you see it coming up as, but like I guess it's arbitrary until you do the parameterizations, and that's when it matters.
Yeah, because when you see the divergence theorem as it's written, there's no parameterization involved.
All right.
It's just you just say, oh, it's got to have positive orientation.
Right.
But you don't really know what orientation you're using until you go to parameterize it and you pick one.
Okay.
And see what you get, and you might have to flip it. And that's what's going to happen in this case. We got to flip it.
Okay.
So yeah, since the divergence theorem requires positive orientation, we need this part normal around here to point down. We need the normal all over the place to point out. But we're not going to be integrating over this part. All right, we're not going to do this directly.
Right.
We're just going to do this, the base, which will be easier to work with because z will just be 0. And then we'll do this, where we're integrating over the interior. All right. So the strategy is this. Even though this was not a closed surface, we go ahead and add another surface to close it. And now we apply the divergence theorem here. We'll actually compute these, and then we'll get this. So we have to parameterize the base. We do not have to bother with this at all. And then here we're going to set up a triple integral. And since we're going to be integrating over the interior of a ball or half ball, for that it's best to use spherical coordinates. Okay. So first, we'll go ahead and do this. Then we'll go ahead and do this. And then we'll combine them to get what we're really looking at. So our answer is going to be 1 minus 2. Or integral number 1 minus integral number 2. Yeah. Okay. So questions before I need to erase this? All right. E, top half of the unit ball, x squared plus y squared plus z squared is less than or equal to 1. Z must be non-negative. So the integral over this half ball, we use spherical coordinates. So 0 to, all right. So we're going to have the divergence of f, which I'll fill in here in a moment. We're going to have our factor that we need to include from spherical coordinates. And then we have d rho, d theta. Make sure they're the same orders in the notes. Okay, actually, I do phi first. D phi, d theta, d rho. So rho is going to go from 0 to 1 because we're dealing with a ball of radius 1. Theta is going to go all the way around, so 0 to 2 pi. Phi, we're only covering the top half, so we go from 0 to pi over 2 because 0 is the north pole, pi over 2 is the equator, and pi is the south pole. We're not going to go that far. So now the integral is almost set up. We just need the integrand. So So a divergence of f. So that's going to be, so the components will be, say, z squared x with respect to x plus 1/3 y cubed plus tangent of z with respect to y plus x squared z plus y squared with respect to z. So we just need to carry out all this differentiation. So we're going to get z squared. Here we'll get y squared. This will go to 0. And then here, derivative with respect to z, that's going to go away. We'll just get x squared. So, worked out something nice. X squared plus y squared plus z squared, which in spherical coordinates is what?
Sphere? Or yes?
Rho squared. Yeah. So that is all that's going to go in here. So this is a relatively harmless integral to evaluate. So I'll just combine these rows. So we get rho to the 4th. Okay. All right. So for these triple integrals, if I come up from a divergence theorem, you not necessarily have to come up with parameterization necessarily. You may have to switch to cylindrical or spherical coordinates. You might have to break them up into more than one integral. So you just have to come up with the appropriate limits, like what we had to do back in the previous chapter. Okay. Now, as happened in the last example, there's no dependence on theta here. Theta runs from 0 to 2 pi. So I can pull out a 2 pi. And there's no more integral with respect to theta. So we're going to have rho to the 4th out here. I pulled out the rho to the 4th. And then from 0 to pi over 2, sine phi, d phi, d theta. Or d rho, rather. Okay. All right, so now we can go ahead and integrate this. So we're going to have minus cosine phi from 0 to pi over 2 d rho. So we plug in the limits, and this whole thing is going to turn out to be 1. So we have 2 pi over 4th d rho. So we have 2 pi rho to the 5th over 5 from 0 to 1. So 2 pi over 5 is the integral for that part. So the interior of the half ball. Okay. Questions? So what happened here, the reason why applying a divergence theorem is a good idea is because when you compute the divergence of this vector field, it's really simplified. Whereas if you were going to evaluate the integral of a normal component of this over the over the top half of the sphere directly, then you'd still have this whole thing in here, all of these components. So what you're going to get, so even though you still have integrals kind of like this over respect to theta and phi, the trouble is the integrand you would get would be so much nastier than this. So you'd be integrating for a long time. All right, so that is part of our answer. But we still need the other part. The integral over the base. So the answer we really want is equal to triple integral of a divergence, which we just figured out, minus the integral over the base. Okay, so this we got, so that's 2 pi over 5. Now we just need this. Now,